So measurement is the comparison of a physical quantity with a fixed standard of measurement, and it has to always include a unit. So some units we're going to see and utilize a lot is centimeter, kilogram, milliliters, and so much more. Now, two qualities of measurement is how precise they are and how accurate, and there is a little bit of a difference with these terms. So precision is how close that number is compared to repeated measurements of the same quantity. So if you're measuring a piece of wood or cutting multiple pieces of wood, you want them to all be very precise or all very similar in measurement. Now, accuracy is basically how close it is to a single measurement. So if you wanted that piece of wood to be 12 inches and 10 centimeters after, you would then make sure that you were as close as possible to that exact number you wanted. So you have to have some sort of frame of reference when you're trying to see how accurate you're being. So we're going to look at some targets here on the next slide, but we basically want to keep in mind that we are comparing the 5 arrows, and each arrow is represented by an X, and we're going to go ahead and describe each target with the descriptions entitled below. So we have here A, B, and C, and we have poor accuracy and good precision, poor accuracy and poor precision, good accuracy, good precision, and good accuracy, poor precision. So if you could try to pause this video and try to label A, B, and C, and I'm going to go ahead and do it with you here in a moment. Okay, so A, let's just see what we have here. So A, again, with a target, this is the center you're trying to hit, right? So that would be if it's accurate. Is this accurate? No, A is not accurate. Is it precise? Yes, very precise. It's all in the same area. So good precision, but poor accuracy. So we're actually going to say A is number 1. Okay, so B, we see here that we have, again, there is 1 hitting the target, but there are 4 hitting the other sides. So we do not have good accuracy, or because they're all a little bit different in different areas. We also don't have good precision. So this is actually going to be number 2, poor accuracy and poor precision. Now, letter C is when you are looking at a target that has all of them in the center, okay, which is what you want to have. So this is a good example of good accuracy and good precision. Okay. Now, we want to talk about how we can measure precision. So we use significant figures, or sig figs, or significant digits when we are trying to understand how precise or accurate a number is. Okay, so significant figures is a technique that we use to represent accuracy of measurements, and we use it as a rounding technique, and we're going to actually use these throughout our entire course. So understanding the basics of sig figs is very important. So let me give you an example here. Say person A is told to measure 12 feet of wood, and person B is told to measure 12.00 feet of wood. So these extra zeros here add a lot extra precision. Okay, so this person measuring 12 feet of wood, you know, with a ruler or some sort of tape measure tool, they would be pretty accurate, right? But if they didn't have that, then they were doing 12 feet, maybe they had a different way of measuring it, it may not be as accurate as somebody that has to hit 12.00. Okay, so these extra digits provide extra precision and accuracy. Now, anytime we are working with a measurement, there is always some uncertainty. So let's say we're working with 2.85 centimeters. The 2 and the 8 are considered certain digits. If everybody measured this piece of wood or this nail right here, we'd all get 2 and the 8. Now, each of us could maybe have a different uncertain digit. The uncertain digit is always going to be this last digit. Okay, so maybe I measured it and got a 5, you measured it and you got a 4, the next person measured it and got a 6. So we would all have the 2 and the 8, but we could have a different uncertain digit. So a digit that has to be estimated, because usually it's between 2 areas you can't really see, and we have that demonstrated here above, is always uncertain, and every single measurement has a degree of uncertainty. okay, because we always want to be as exact as possible. Now, we are always going to write down every single necessary number. So if we're using a balance in lab, we write down everything that we see, okay? We never round any actual measurements given to us. So if we had a number down below, for example, 46.71, the 4, the 6, and the 7 are going to be called the certain digits, and then this 1 right here we know would be the uncertain, okay, or the estimated digit, and that is the one that could have some plus or minus error. All right, so there are a bunch of rules for measuring sig figs, and we're going to walk our way through these and then also look at some examples here. So non-zero integers, which just means numbers, always count as significant. So we're going to be counting how much significance values have. So for an example, 3,456, each one of these is considered significant, so it has 4 sig figs, and we just round that instead of saying significant figures every time. So here we have another example, 7,834 has 4 sig figs. Okay, so 4 pieces of precision, so it's a pretty precise number. Now, the confusing part in sig fig rules are the zeros. So we're going to look at some different cases of zeros, zeros in front, zeros in the middle, zeros at the end, and they all have different rules. Okay, some are significant, some are not. So something that has leading zeros. So leading zeros means zeros that precede any non-zero digit. So all of these are leading zeros. Okay, they are never significant. We do not count them in our sig fig measurement. So for example, 0.048 has only 2 sig figs. And if we have another example here, 0.00766, this only has 3 sig figs. Now, that does not mean that we do not write these zeros, because obviously they're very important, but we do not consider them as part of the precision. Okay, so this is 3 sig figs, and the previous example was 2, but we will still see those written in our average number. All right, captive zeros. Those are zeros that are in the middle. So let me demonstrate to you what that means. This is a captive zero, and these are always between non-zero digits. So it's between a 6 and a 7. And the one down here, this is a captive zero. These are captive zeros, and they're between non-zero digits. Okay, and they are always considered significant. So that means when you start counting sig figs and you have a captive zero, you keep counting. So this is significant, this is, this, and this is. So we have 4 sig figs. And remember, that last digit here is always called our estimated digit. So I just wanted to review that term with you. Now this one, 1, 2, 3, 4, 5, 6. Okay, so 6 sig figs on that one. So again, when you start counting and they're in between 2 non-zero digits, that zero is. All right, trailing zeros. Trailing zeros are zeros at the end, and they are the trickiest to figure out if they're significant or not. So trailing zeros with a decimal point. So the decimal point really here is the big sticking point. So because this has a decimal point, that makes these trailing zeros significant. So 9.300 has 4 sig figs, where 9.3 only has 2. Okay, so this decimal place makes these trailing zeros significant. Now 150 with a decimal point here makes this significant as well. So this has 3 sig figs compared to just 150. This is also a trailing zero without a decimal point, so it's only 2. So please look at the difference here. The decimal point, which you probably prior to this lesson did not realize was so important, really does have a big effect in precision. So here we go again, trailing zeros without a decimal point are not significant. So again, this is just 2, and this would just be 3. Yep, you put a decimal point at the end of those, and it would change the number of sig figs. Now this is a pretty easy one. Anything with an exact value that is not a measurement has infinite number of sig figs, and we actually just use the infinity sign, or we write the word infinite. So if we were counting 17 people or 10 dogs or 22 paper clips, anything that has a unit after that is not a measurement, not grams, not meters, not liters, has infinite, because if I asked you to count these 5 paper clips and I counted 5 paper clips, there's infinite precision because there is actually 5 paper clips, right? Where if I gave you a piece of wood and have you measure it, you might be a tiny bit different with that uncertainty digit at the end than I would have. So that is the difference. Something with a unit that is not a measurement has infinite sig figs. Okay? Now, counting sig figs, why don't you go ahead and utilize your rules and try to work on these examples here on the left side. So pause the video and try those. I'm going to go ahead and do them with you, and then we're going to practice rounding as well. So we have 4 sig figs here. We have 3 sig figs. 4, 3, and all 5 here. Okay. So again, all of these, if you're confused about the zeros, please go back to the rules. All right, so let's go ahead and round. This is more what we're going to do. We're going to learn how to round and when we need to round sig figs. So right now we're being told how many sig figs to round this number to. Other times you're going to have to know for yourself, which I will teach you how to do. All right, so when we are rounding for sig figs, we are going to go ahead, and I like to first circle the amount of sig figs that I'm trying to round to. So this is 2. So my first 2 sig figs is this 1 and this 2. Okay. Now I cannot just cut this off at 12. That doesn't make any sense. If you had $125 in your bank account and you're cutting it to 2 sig figs and your bank rounded you to $12, you'd be really mad because that's not a good round, right? Rounding has to be close to the original number, so always use that as a check. Now, remember, if it's 5 and above, you round up. If it's 4 and below, you keep it at the number that it is, and you always look at the next number. So I'm going to look at this 5. That's going to round this 2 up to a 3. So I'm going to go ahead and round this to 130. Okay, so 13, instead of it being a 1 and 2, it's a 1 and a 3. Now, when you're rounding, you can add zeros to the end without a decimal point to add the tenths, the hundredths, the thousandths place to make sure that you are around the same value. So ask yourself at the end, is 130 close to 125? It is. How many sig figs here? 2. Therefore, you're good. Okay? All right, so let's do this again. 0.00285, rounding to 2 sig figs. My first 2 are the 2 and the 8, although these zeros do need to be shown. You do not cut out zeros that are not significant. Okay, so 0.00. Now this 8, you always look at the next number. The 5 is going to round it up, so we're going to put 0.0029. So that rounds me to 2 sig figs. These are not significant, right? They're in the front, but this 2 and the 9 is. Okay. All right, we're going to go ahead and round this next one to 3 sig figs. So my first 3 is 1, 4, and 6. The 5 is going to round this up. We're going to go put 1, 4, 7. But again, 147 isn't close to that, so we're going to go ahead and round that to 1,470. Okay. All right, 1 sig fig. We have a 3. Do we round this up? We never just cut. We always look at the next number. That 5 is going to round that 3 up, so we're going to go ahead with 4, and we have to use zeros to replace the rest. Okay? Again, ask yourself, is 40,000 close to 35,000? Yes. Okay, so you know you're at least in the ballpark. All right, so this last one's a little bit more difficult. 4 sig figs. So our first 4 is the 2, the 8, the 4, and the 9. The 5 is going to round up the 9. And the 9 is going to round up the 4, okay? So let's just see what we would assume this to be, and then we'll check it. So we're going to say it's 28,500, okay? The issue is that's only 3 sig figs. We need 4, so something is not going to work by doing this. Now, if there's no way to make your number into the amount of sig figs you need, you can always utilize scientific notation. So if you don't remember scientific notation, please YouTube it or look in your textbook. But we're going to go ahead and try this again. We are actually going to put this number into scientific notation. So I'm actually going to do that right over here. So if I were to put 28,495 into scientific notation, it would be a 2.8495 times 10 to the 4th. Okay, moved 4 spots. Now, we can go ahead and make this a lot easier on ourselves to make it 4 sig figs. Again, underline our first 4. We're going to go ahead and change that to 2.850 times 10 to the 4th. Now, this times 10 to the has no effect on significant figures. We didn't really talk about that, but this times 10 to the, although it's important to have, it does not add any significance. So again, let's just check this. How many sig figs? 1, 2, 3, 4. Perfect. This N0 is significant because of the decimal point, and this, although important, we're going to always write it. It's not considered part of our significance. Okay? All right. Now, again, how do we figure out how many sig figs our answer should have? Let me show you. So if you are adding or subtracting, so there's different rules for adding and subtracting compared to multiplying and dividing. If you are adding and subtracting, you are going to round your final number to the one with the smallest number of decimal places. So let me show you what I mean here. If we have 111.45, this has 2 decimal places, and 16.2 has 1 decimal place. So we do not do anything first. We get the original number, we add or subtract. In this case, we were adding. After we get this number, we round. So we want the answer to have 1 decimal place. So we keep the 127, we look at the next number, the 5 is going to round this up, and we end with 127.7. So all we look at for addition and subtraction is how many decimal places and rounding to the smallest number of that. Now, the rules for multiplication and division is a little bit different. This is more what you're going to utilize. For multiplication and division, the number of sig figs in the result is the same as the one with the smallest number. So you look at your math, you have a number with, this is wrong, this should be 4 sig figs, please excuse me here, 4 sig figs, and then you have, all of these are significant, 2.65 with 3 sig figs. Okay, then you go ahead and do the math. Again, you do not focus on sig figs until the rounding aspect at the very end. So this is what the answer is in the calculator. And then let's round this to 3. I like to underline my first 3 and then look at the next number. This 0 is not going to increase this. So I'm going to go ahead and round this to just 385. Okay. So do the math, round to the lowest number of sig figs. We do not look at decimal places here when we're doing multiplying and dividing. All right, so let's go ahead and look at a couple of the math components here. So when we are doing things that have multiple actions, so for example, it has addition and subtraction and multiplication and division, we are going to kind of round at different points. So go ahead and read those steps, but I'm going to go ahead and demonstrate here below. So if we have 31.25 plus this 0.3, right here is an addition. So we would do that math first, and we would use the addition and subtraction rule, which is the one that has the least number of decimals. So we'd round this answer to just 1 decimal place. And then we would take the answer to this, which is 31.6, and multiply it by this value. So that is then a multiplication rule. So then we want to count how many sig figs. This has 2 sig figs. And this has 3 sig figs, so we always do the least. So the answer is going to be rounded at the very end to only 2 sig figs. Okay, so when you have multiple different mathematical steps, you want to kind of do it in pieces. Now, if it's all multiplication or all division, you can round at the very end. If it's all addition or subtraction, you can look at the decimal places at the end. But if it is multiple actions, you need to do each step individually, okay, and round and then use it on the next one. So we're going to go ahead and do a little bit of math here. We are going to look at this calculation here. We have 6.8914, and then we have divided by 1.289 times 7.28. So we're going to go ahead and first do our math, okay? So I'm going to go ahead and get my calculator. Make sure you have a calculator out for this. And we're going to go ahead and do now there's no parentheses here, but I like to do the bottom first. So I'm going to go ahead and do 1.289 times 7.28. And on this bottom, I get 9. I'm not going to do any rounding here. I'm actually going to write the whole number, 38392. So my new problem is this 6.8914 divided by that. I'm going to go ahead and type that into my calculator. 0.38. Okay, now when I divide this, my calculated answer is 0.7343839, and there's a lot of extra, but I know I'm not going to need more than that, so I'm just going to go ahead and write that. Now let's round sig figs. This is all multiplication and division. So let's see, this has 5 sig figs. I'm going to go ahead and write a little 5 here just to show. This has 4 sig figs, and this has 3 significant figures, okay? So the one that has the least number of sig figs is the one we're going to round to. So this one has 3. Let's round our answer to 3 sig figs. My first 3 is these. So 0.73. Does this 3 round this 4 up? It does not. So my answer is 0.734. Okay, so do the math, then do the rounding at the end. Let's try another one here. And this has multiple different components. So we're going to look at, we have some subtraction here, and we also have some multiplication. Let's go ahead and do the subtraction first, because that's in parentheses. So go ahead and take the 0.456 minus the 0.421. And I'm going to go ahead and write my answer above for this, 0.035. And let's go ahead and look at our rules for subtraction. It's the least number of decimal places. These both have 3 decimal places, so I'm going to keep this number as 0.035. And then I'm going to go ahead and multiply this by 92.35. And I go ahead and my calculated answer is 3.23225. Now let's see. Sig figs wise, this has only 2 sig figs because that front 0 does not count. And this has 4 sig figs. So my least number of sig figs is 2. Let's go ahead and round this answer to 2 sig figs because we're always doing the least number. My first 2 is the 3.2. Okay, so my answer is 3.2 for that one. That finishes us off with sig figs and the rules for multiplying and dividing and adding and subtraction.